So hopefully at this point we now have a better understanding of the way binary search trees uh, wor- work based on their properties. The consequences of this, the fact that that these binary search trees are sorted, is that the values in them are sorted and we never have to sort them, right? Since everything to the left of of a root is less than the root, and everything to the right of the root is greater than the root, and that continues down recursively, the tree is always kept sorted for us, which means that we never actually have to go through and sort it. Whenever we add something or remove something from the tree always maintains its order. Um, so, in a binary search tree, ideally, if we get this thing entirely balanced, a phrase that I'm not going to define on purpose, which may be a hint that might occur somewhere later. When a binary search tree is properly balanced, which basically means that both sides have about the amount of same number of nodes, then by going left or going right to search for an item, right, by going down, choosing a branch, we essentially eliminate half our search space that we have to look at. This means that if we're looking, right, this essentially means this is the same algorithm that we use for binary search. So we have eliminated half our search space at each step, so it's going to be a log n lookup type. In the worst case, searching is O of n. Now, how could that possibly happen? Well, let's go ahead and just draw a basic diagram of that, how that could happen. We could get something like this, where I insert as we'll learn with our algorithm, with our addition algorithm, we could add in our first item, and it could be 1. Then we could get another item 2, another item 3 over here, right? And the children, and it could be everything we'll learn. It could be added in such a way that basically that there's no left children and there's only right children, or there's only left children and no right children. In which case, searching would be O of n time. Essentially, if our tree looks more like a linked list and less like a tree, that's our worst case scenario. But most of the time, it's going to be log n, every single operation. This is add, remove, contains. Okay? And the way it does so is it uses what I've referred to as the zigzag algorithm. So this is the first of the two algorithms that you need to master for trees, and it's very easy. Base case, if the tree is empty, we return null because we couldn't find what we were looking for. Otherwise, if the target that we're looking for matches what's in the root, we return the data stored at the root node. Otherwise, if it's less than the root, we look at the root of the left subtree. If it's if the item we're looking for is greater than the root, right? If it's not equal to, it's not less than, it has to be greater than, then we look at the right subtree. That's essentially it. That's the entirety of the algorithm. We're going to use this algorithm for both add and for both remove, right? So add and remove, contains, all will do this. We'll all use this. So that kind of begs the question of, well, that seems to be everything, so what's the other algorithm? And the other algorithm is traversal, which we'll get to in just a minute. And that's going to be used for things like toString. Right. So now we're going to go over the final definitions, two of which are really easy. One is the more complex one, but I'll be going over the examples for that.